Before evaluating the position at the end of segment 1, let's look at some other Hackenbush positions which may be more instructive. How big is this game? Let's call it X. Whether he goes first or second, left can win, so X is positive. But from X minus a half, right can win, so X minus a half is negative, and X is between 0 and a half. Since we can add inequalities among games, X plus X is between 0 and 1. Since a half is also between 0 and 1, the natural question is to compare X plus X with a half. A quick study of this game will reveal that either player, going second, can win. So X plus X equals a half. Let's now prove that. Suppose that blue starts by playing on the branch lettered A. Then red can respond with the scissors shown, leaving the position from which we claim red can win. To see that, we notice that if he takes the dotted branch, he reduces to a position of value 0, which we have examined before. Or, if he goes second, he can just ignore the dotted red branch throughout the game. Similarly, if either player plays the red or the blue scissors as shown, then the other player can respond with the opposite, leaving a 0 position from which the second player can win. Hence, every lettered opening move can be defeated. These two moves also cancel each other out, so letter C as well as letters B and A are all losing moves for the first player. Similarly, we can see that red's opening move at D is no better for him than C, and E is no better for him than B. So what if red begins by playing at letter F? This creates a position in which only blue branches touch the ground, and we will soon show that that is part of a theorem which under such conditions shows that the graph is positive and therefore a win for blue. Hence, an application of that theorem will show that every lettered move loses, and therefore the initial position X plus X minus a half is a win for the second player, which is 0. Therefore, if X is a number, it must be equal to a quarter. So let's now go back and prove the theorem that if only blue branches touch the ground, position is a win for blue. Giving a hint as to its proof, this theorem is called the lawnmower theorem. Here is a typical example. We begin by reorienting the graph in such a way that blue's branch, which touches the ground, is shown at the far lower right of the figure. If it's blue's turn, he brings in his scissors as a lawnmower and cuts the leftmost branch touching the ground. Red plays anywhere he wants. Blue's turn, again brings in his lawnmower scissors and still cuts the leftmost branch touching the ground. This process continues for as many moves as needed until the only branch touching the ground is the blue branch in the lower right. When blue eventually takes this branch, it ends the game and he has won. This proves the lawnmower theorem. In the first segment, I said there are some Hackenbush positions from which either player going first could win. Here are 3 examples. These examples were composed in such a way that if we add them all together, we get a harder 4th example, but it's yet another position from which the first player can win, no matter which player that is. We'll now show that at any such fuzzy example, at least one of the 2 players' opening moves must be to take a branch which is colored green. In particular, if blue can win by taking a blue branch on his first move, then the game is positive. Here's such an example. Here's another, much harder example. And here's the general case which covers them both. Since blue's opening move from G to G' leaves a winning position for him, G' must be greater than or equal to 0. And since the red moving second from G had no winning move, G cannot be 0, so it must be positive. Similarly, if red has a winning first move on a red branch on G, then G must be negative. This yields the following corollary. If a Hackenbush graph has no green branches, and either blue or red has a winning first move, then the game is positive or negative accordingly. If neither player has a winning first move, the game is 0. Hence, no Hackenbush graph without any green branches can be fuzzy, and all sums and differences of such graphs again have no green branches. So the set of all Hackenbush graphs with only blue and red branches is totally ordered. They behave exactly like the ordinary numbers, so we'll say they are numbers. How big are these numbers? In the first segment, we saw that the two-branch string LR, consisting of a blue branch supporting a red one, was equal to 1/2. Then a couple minutes ago, we saw that the three-branch string, reading from the ground up as LRR, is equal to 1/4. By extending that same argument, we can conclude that the four-branch string LRRR is equal to 1/8, and so on. The proof requires only that we verify that for any value of the positive integer n, the sum of the strings LRN and another LRN is a one-branch shorter string RL to the n minus 1, yields a sum which has no winning move for the first player. So it is 0. Hence this string, which is LR to the 7th, gives a small advantage to blue. More precisely, this small advantage is 1/128th of a move. The beginner may find it a good exercise to test a few implications of these results. Since we now know that blue and red Hackenbush positions are numbers, but those which also contain green branches are usually not, we'll next show how an arbitrary Hackenbush position can be decomposed into a sum of smaller graphs, each of which may be easier to evaluate. A Hackenbush position's purple mountain is defined as whatever remains after all green branches are removed. Here's an example. We cut all green branches simultaneously. We then remove every branch no longer connected to the ground. The purple mountain is what remains. Since it contains no green branches, it must be equal to an ordinary number. We next define the green-stemmed jungle, more simply called the green jungle, even though it may contain blue and red branches not connected to the ground. To this end, we recolor all of the branches in the purple mountain as black. On this graph, we've also lettered the green branches. We then let the black branches join the ground. This graph is then called the green jungle. If we add 2 to the minus k to the green jungle, the result must be positive because blue controls the ground. On the other hand, if we add minus 2 to the minus k to the green jungle, the result must be negative because now red controls the ground. Hence, the green jungle is between minus 2 to the minus k and plus 2 to the minus k. Since this must be true even for any very large positive integer k, we conclude that the green jungle is an infinitesimal. Like any game, the infinitesimal might be positive, or negative, or zero, or fuzzy. Here's an example of each. But whatever its outcome class, the infinitesimal green jungle will have only an infinitesimal effect on how much the total graph differs from its purple mountain. But any move on the purple mountain will change the value by a numerical amount adverse to the mover. So in the full position, neither player will move in the purple mountain until the green jungle is entirely gone. Hence, the full position is equal to the sum of its purple mountain and its green jungle. To conclude this segment, let's look at this overview of the solution of the game at the beginning of segment 1. The green jungle and the purple mountain are each 0, and so is their sum. In the original position, a good player can let his opponent play either color, but against a good opponent, he has no chance of winning unless his opponent makes the first move.